Hey everybody, in this video we are going to talk about the electric field. First, let's recap what we talked about today in class. We saw that if we are close enough to the Earth's surface where we can approximate it as being flat and infinite, that then the Earth has a gravitational field downwards, and that gravitational field for the Earth has a value of approximately 9.8 newtons per kilogram. I do need to emphasize that this is an approximation. The Earth is not actually flat, but because we are small relative to the radius of the Earth, we can approximate it as being going in infinitely to the left-right directions, and it being approximately flat for our purposes. So the G field looks like this. And then we compared that to what if instead we had a metal plate, and that metal plate had a negative charge on it. Well, in that example, we said that the electric field would be downwards, and the electric field would have a magnitude of some number of newtons per coulomb, not kilogram anymore, where, I don't know, let's say it's 7 maybe, newtons per coulomb, just some number. And this tells you the force that some other third object would feel here, some test charge, per coulomb of charge that this test charge has. So for example, if this test charge is a charge Q naught, then the electric force on that charge would be equal to the test charge multiplied by the electric field strength. You take your newtons per coulomb of electric field strength, multiply by the charge in coulombs, and you'll get the full force. This is the electric equivalent to the gravitational force being approximately equal to m times g on Earth. This is where we ended class, and we did a lot of examples to get the intuition for what this electric field strength quantity is measuring. There's some additional things I want to throw out there. A negatively charged plate down below will have the same field strength as a positive plate from above. And that's, again, the infinite flat approximation. It will have an electric field this way because if we put a positive test charge in this space, then that positive test charge would be repelled by this plate. Or more generally, if we have a negative plate down below, and if we have a positive plate up above, then we can amplify the strength of that electric field, and it would still be uniform. Now, it's only approximately uniform in the zone where you're not near the edge, and these look infinite, and it kind of will bow out a little bit when you get near the edges. These arrows tell you the direction of the electric force on a positive test charge. So let's write that down. Electric field lines, or I guess they tell you the path that a positive test charge will take if it starts from rest. This is a big if. And we'll look more at why that's a big if later on. And then the other fact here is that the electric force on the test charge, that arrow will be tangent to the electric field line. Whoa, electric field line. I cannot spell right now. Woof. Electric field line. Woof. There we go. All right. So there's some facts. And so if we want to, and the reason we looked at this positive plate on top and negative plate on bottom is because often this is the easy way to generate a uniform electric field using a circuit. You can remove the electrons from one plate, add them to another, and then you've got yourself your uniform electric field. This setup is named a capacitor, and we'll talk more about this setup later on. Specifically, it is a parallel plate capacitor because it's made of two metal plates that are parallel, and you can use a battery to separate the electrons off of one plate and put them onto the other to get this electric field. All right, what about some other scenarios? We also saw in class today that if we zoom out from the Earth and we can approximate the Earth now as a point particle, so we're really far away from the Earth. Why can't I spell today? Wow. Particle approximation. So if we can approximate the Earth as a point particle, then the electric field lines will point in, or the gravitational field lines for the Earth will point inwards. And if we wanted to compute the strength of the gravitational field strength, we would take the gravitational force divided by some test mass that we threw out into that space. And we watched it drop. Now the gravitational force, this is to write it a bit easier to see the next line, we'll write it as 1 over the test mass multiplied by the gravitational force. When we're approximating the Earth as a point particle with its mass concentrated at the center of mass, the equation that we need to use for the gravitational force is Newton's gravitation constant times the mass of the Earth times the mass of our test object over the distance between the center of the Earth and the test mass squared. Now, we're looking for a result independent of this test mass, regardless of what it is, which is why we divided it out. And what we're left with is the general equation for a gravitational field, which is big G times the mass of your central body, which is the Earth in this example, divided by r squared. And if you plugged in the radius of the Earth and the mass of the Earth into this equation, you would end up with 9.8. So, we know how to do this for gravitational forces. Now, what if we have point charges? So the electric field due to a point charge. This is not in general what an electric field is. This is a specific equation that we'll use if your source for the electric field is a point charge. So let's say we have a positive point charge, let's actually do negative first. Got ourselves a negative point charge. If we put a positive test object, small little test charge, it would be attracted, and so we know that the electric field lines are going to point radially inwards, and we'll call these the electric field lines. Maybe I should label the Earth as gravitational field lines on the left there. And we can follow a similar procedure, now that we've defined the electric field, to come up with an equation for what the electric field strength around this would be. So it's going to be the electric force dividing out the charge of that test charge to make it independent of that test object. And we know that would be 1 over Q naught times Coulomb's constant K times Q, we'll call it, Q of the object times Q of the test object divided by distance squared. And so if this central body has a charge negative Q, then what we're left with is the test charge canceling out, and the electric field strength due to a point charge, its magnitude will be equal to KQ over R squared. The equation would be the same for a positive test charge, but the electric field would radiate away from the center rather than toward it. And I want to put a wall between those two to say that they're separate right now. So the picture would look the equation would be the same because the derivation would be the same, but the direction would be different. So in this equation, we just want to plug in number of charge, not its sign. And then we'll use our brain to determine direction. All right, so this is what the electric field around a point charge would look like. We can see that there's an inverse relationship with the distance squared. And so what that means is that the electric field gets stronger the closer you get to its source. So electric field gets stronger. Let me back up. The electric field due to a point charge. This is a specific example, right? Due to a point charge gets stronger the closer you get to that charge. And how are we going to visually see that? Well, we can see with these field lines, the closer we get to the object, the number of lines doesn't change, right? There's 8 lines no matter where you are. But the closer you get, the more dense the lines are, the closer they are. If we look here around this circle, the lines are close together. And if we look here at this bigger circle, the lines are more spaced apart. And so the field strength, the strength of the electric field is represented by how close neighboring electric field lines are. Electric field lines are. So that should be a pretty good summary of what we're talking about. We can see in our uniform field that the spacing between the lines is roughly evenly spaced until we get out to the edge, which gives us that approximate uniform field. Here, when we can approximate things as point particles, we see that the closer you get to that particle, the closer the line gets, and the electric field follows this equation. So I think that'll do it for this video. I'll make another video on the electric field lines around what will be called a dipole arrangement, and I'll do an example problem or two as well.